Let us now start out by extending what we had discussed in the previous slide set. So there we had established an equivalence between a parallel execution and a sequential execution. All right. So 1 second. So we had said we had given this criteria, but we had not extended the logic further to actually create a correctness criteria or to say that when a given outcome is valid or not. In a certain sense, this was not extended to a memory model. So let us create our first memory model called sequential consistency or SC. So this is fairly old, and this was pretty much the first widely accepted memory model to be proposed in the late 70s by Leslie Lamport. It is the most intuitive yet the most impractical. So let me read it out. It's an easy definition. So when a parallel execution is equivalent to a legal sequential execution, and the order of operations in the sequential execution is as per program order, we say that the execution is sequentially consistent. So what are we doing? We have a parallel execution. So we say that for each thread, let's order them in program order. So this is the typical diagrams that we have been drawing, where each circle represents an operation. Then we define an equivalent sequential execution where the criteria for equivalence was specified, where essentially we take all of these operations and we arrange them in a linear sequence with a one-to-one correspondence, right, subject to the fact that the orders remain the same. So a further caveat is that yes, this needs to be legal sequential execution, and second, this order needs to be as per the program order of the thread, right? So because program order across threads makes no sense, but within the same thread, of course, the program order is the order in which we fetch instructions or the order in which we retire instructions. So since that is in order, in program order, we say that the order in the final sequential execution, which is also this order in the parallel execution, this has to be as per program order, and the final sequential execution has to be legal. If it is possible to convert such a parallel execution into such kind of a sequential execution with these two properties, one, it is legal, and for every thread the operations appear in program order, then we say that the parallel execution is sequentially consistent, or it is an SC. So we can say that formally the execution is an element of SC, which means that it is sequentially consistent, or in other words, it means that it is possible to take a parallel execution and sequentialize it in this manner. So we will get into the deeper meaning of this, but we can visualize this differently. So if you would recall the previous slide set, what we were actually doing is that we were taking operations issued by different threads, and we were trying to interleave the executions. So we were saying we take an operation from thread 1, another operation from thread 2, another from thread 1. So we were trying to create a sequential interleaving, right? The same way we interleave our fingers. So this was creating a sequential execution, right? So this will be considered a sequentially consistent execution if number one, it is legal, which means every read receives the value of the latest write. So latest and non-latest in a parallel world means nothing, but in a sequential world, the latest write is easy to find. We just walk towards the left and we find the latest write to the same address. And in each thread, the operation, so for each thread, so let's say if I take a projection with respect to a certain thread, for each thread, the operations appear to be in program order. So we can say that this predicate holds true for every thread. That the sequential execution projected on every thread, they appear in program order. And this is the same, this will be true for the parallel execution as well with legality. So if we think about it in a deeper way, let me just erase the ink on the slide. So this in a sense captures the intuitiveness of what we have been trying to say. So what are the key properties of SC? Well, the key properties are that we take two threads. I'm going to derive the two properties, right? So let's consider a two-threaded system. We have operations. We just create an interleaving of them. So let's say these operations are, let's represent them by circles, and let's represent these operations by squares, right? Sorry, by rectangles. So any of these interleavings is going to be represent a sequentially consistent outcome, right? As long as we interleave them in a certain manner and the execution is legal. And of course, the interleaving is as per program order. So as you can see, a sequentially consistent outcome can still have a sequentially consistent system can still have multiple outcomes, that is fine. But all of them have to be produced via an interleaving where two things are preserved. One is legality and the other is program order. So I have written this in a slightly different manner. So when I say that I can arrange all the operations on a sequential timeline, essentially it appears as if the operation appears to execute at some instant of time between the start and the end. So I can say that all the writes in particular are atomic, right? So reads of course do execute at one point in time because they read the value of they read a value, and essentially a read is a private operation for a core, but a write is meant to be visible to everybody, and all the observers and all the cores agree on a precise time of the write, which in any case is a direct corollary of the fact that I can arrange these operations sequentially. So if I can arrange these operations sequentially like this, then what I say is that look, if there is a write over here, all the cores in any case agree on this order of operations. So I can say that there is a unique instant of time, a precise specific instant of time at which the write appears to complete, which means that any point in time or any operation before this point in time doesn't see the write, and all operations after this point of time see the write. So whenever an operation completes instantaneously, we say that the operation is atomic. So of course, as I said, a read by definition is a private operation in the sense I read something, I keep it, nobody else sees it. And in a sense, whenever I read it at one point of time, when I get the value, it appears to execute at that point in time. So that's not a big deal. But writes being atomic is important because everybody should agree that a given write was visible to the world at a precise point in time. So this does happen in the sequentially consistent memory model, because when we arrange everything on a linear timeline, a write has to appear to happen at a given point in time. So the key word that I would like to use is the word appear, and you will often see this word in the concurrent systems literature, where the way to actually understand this is that all the threads agree that look, there is one instant of time. It doesn't matter whatever that instant is, but at least the instant of time exists, right? So it's important. We don't care what instant of time it was, as long as all of us agree that look, there was a point in time where the write executed instantaneously, and this and all the reads after that will get the value of this write after that to the same address. So this is legality, and legality in this case is transferring to the fact that writes are atomic. Okay. The second is program order is preserved in the sense in the final sequential execution, which is equivalent to the parallel execution. For each thread, the operations appear in program order, which is anyway the order in which we were interleaving in our discussion in the previous slide set. So this is intuitive, this is intuitive. So all that sequential consistency does is that it takes two of our intuitive notions of legality and program order. Legality gets converted to atomicity, and it combines atomicity and program order. And lo and behold, we have our first consistency model called sequential consistency, which given a parallel program will give us a set of valid outcomes, which to our mind are intuitive. In a sense, it's all a question of taking the instructions of different threads and just interleaving them. So the key word here is interleaving. I would request all of you to thoroughly understand the meaning of this, pick up a dictionary, and the meaning of this is that I maintain the order of each thread and I just interleave them the way I have done over here. So this is a very important correctness criterion. And so let's say that this is the gold standard of all consistency models, where this is clearly the most intuitive, right? So in terms of intuition, it is very high. And in terms of common sense, sequential consistency appears to be the way to go because it gives us a very simple property that take a parallel execution. As long as you can convert it to a sequential execution with these two properties guaranteed, which appear to our innate sense of reason, we can say that the execution is correct, we can reason about it. Anything outside that, we will say is a non-SC. Now here is the sad part, this is why I say it is impractical, because almost all the optimizations that we have proposed break SC, right? So let they be out of order processors, MSHRs, you name it. All the cache, NOC and core optimizations that we have proposed, they either break program order because loads are issued early. Some of them, particularly the ones that we will discuss in this chapter, as well as methods that use the NOC, will break atomicity. So that's the reason there is a problem. So here again I would like to say that if a single threaded program is executing on a multi-threaded, if a single threaded program is executing on a multi-core processor, the results will be identical to that executing on a unicore processor. For single threaded, there is no issue. The issue arises for multi-threaded programs that share variables, because if we reorder accesses to different addresses, so recall this example that we had given in the previous example, in the previous slide set, where this is what we had: x is equal to 1, y is equal to 1, we read in y and we read in x. So from the point of view of this program, we can reorder the accesses, in the sense we can send y first and send x later. As far as we are concerned, this program is correct. Compilers can also reorder, the processor definitely will reorder, and it will not change the final state or the outcome of the program, because these are all, after all, accesses to different variables, right? But as we see, this will create havoc in multiprocessor systems, because this harmless reordering that we have been doing up till now, and that too very carelessly, without any concern for what would happen in a multiprocessor system, this will actually create a lot of issues, in the sense it will directly break sequential consistency. Because if we reorder these two instructions, send the loads early, we can read both T1 and T2 to be 0 and 0. And as you can see, this execution is clearly not sequentially consistent. So let me maybe erase some part of it which is not relevant. Alright. So as we can see, this execution over here is clearly not sequentially consistent if we allow reordering, because program order is not being preserved. But sometimes for performance we break it, and this is where it appeared to be a perfectly great thing to do when we were discussing an out of order pipeline. But when we consider multiple cores, we see that the intuitive correctness notion of sequential consistency cannot be guaranteed. So the main idea is you do something good somewhere, something bad happens somewhere else. So we did great things in the memory system and pipeline. Something bad happened when we start writing multi-threaded code. So let us look at a few examples to understand and also to further to have a slightly deeper discussion. So let's first take a look at single variable programs. Okay. So in single variable programs, we will not have this reordering because they were two different variables. So for single variable programs, let's look at this example where I write 1, then write 2. So thread 1 reads 0 first, then 2 reads 1, thread 3 reads 1 first and then 2. This execution is in SC. Why? Because as you can see, we can order them, a sequential ordering exists, Rx0, okay, Wx1, Rx1, Wx2. So at no point of time have we broken program order yet. Rx2 of thread 2, Rx2 of thread 3. So this is a legal ordering, it's an equivalent ordering, and we have not compromised on program order. But let's take a look at this. Wx1, Wx2. So thread 1 writes 1 and 2 to x. But thread 2 reads 1 first, then 2. Thread 3 reads in the reverse order, 2 first and then 1. So a little bit of a homework, kindly verify. This execution is not in SC. It is not possible to come up with an equivalent sequential execution for this parallel program, which is legal and preserves program order. And regardless of whatever you do, you will not be able to come up with an equivalent sequential execution. So this execution is not in SC. Furthermore, if you look at it, this behavior is non-intuitive because for the variable x, there appear to be different storage locations. For the same variable x, it appears that there are different storage locations in the sense. So here again, the observer is at the level of the thread. So you are essentially looking at it from the point of view of software. So it appears that for one location, it sees the correct order of writes. But for the other thread 3, for the first thread 2, it sees the correct order of writes. But for thread 3, it sees the writes in the reverse order. So somehow the updates to X are getting garbled up, and that is not really what you would expect to see in a shared cache that has a single location for X, because any observer who's sitting on X would essentially see 1 written first and then 2. Thread 2 would agree with this, thread 3 will not agree. Hence thread 3's execution is not valid. So what we see is that, now we are kind of looking at the finer points, that for a single variable program, or let's say if I consider all the accesses to a single variable in a multivariable program, if SC is not guaranteed, it appears as if we do not have a single storage location for X. And this is something that we explicitly wanted to ensure when we said that for an outsider, a shared cache should appear identical to a distributed cache. Right? So this is something that we wanted to ensure. But you can clearly see that if we have an execution of this type, this is not being ensured. Now, is there a connection between a shared is equal to distributed and SC? Yes, there is. And this connection is very interesting. This is called PLSC, which I will define now. So if we consider all the accesses to a single variable or a memory location, which is X in this case, let such an execution be always in SC. This correctness criterion is known as the PLSC constraint. PLSC stands for per location sequential consistency. It is needed to provide the illusion of a single memory location, even if we have a distributed cache. So what is it that I am doing? What I am essentially doing over here is I am saying that, look, consider a shared cache which is slow and inefficient, but for the variable X it has a single location. Place our friend who's an observer over there. So our friend will observe at this location a sequentially consistent execution, right? Uh, Primarily because your friend will basically see requests coming in, and then it will be legal. So definitely this kind of an execution will not be seen by an observer. And even if, let's say, we are observing this cache from outside and only tracking accesses to a single location, so we will see that, look, this is the shared cache. We are pumping in accesses by different threads, and let all of them be to the same location. Let's filter them out that way. So if it is not in SC, it will appear as if, look, maybe we don't have a single physical storage for X, and something really strange is happening in there. But if we genuinely have a single location for X, it has to be sequentially consistent unless accesses are reordered. So let's assume for a single location that's never the case. Then if they are not reordered, then the only thing we need to guarantee is atomicity or legality. And it will be legal because it's a single location, right? So whenever I read, I am bound to get the value of the latest write. So for a single location in a shared cache, if I'm observing, right, I will see it to be sequentially consistent. Hence, the PLSC criterion is necessary and sufficient. Of course, this is an informal proof, but there are more formal reasonings in the book. But what you need to take away from this discussion is that the PLSC criterion is both necessary as well as sufficient to ensure that a shared cache appears to an outsider the same as a distributed cache, or rather, putting it the other way, the distributed cache appears to an outsider the same as a shared cache, because per location all the accesses are sequentially consistent. So it appears that we have a single location. Whatever the observer at that location will see, an observer outside the cache will also see that, look, requests are going in, they are being serviced in program order, and second, every read is getting the value of the latest write. So the PLSC criterion for us is important, so we will not compromise on this. But the PLSC is not the same as SC. Okay, PLSC is only per location, and there is a deeper connection between them. We will discuss this in some time. But the key thing is, this is something that we will not compromise on. So SC, of course, for SC is a general thing for multiple locations, and there we found that, look, a lot of our optimizations are not guaranteeing SC. Fine, fair enough. But per location sequential consistency, let us strictly disallow this behavior, and let's say that we will always have it such that a shared and distributed cache appear identical to outsiders. How to ensure it is a separate question, but let's at least have it as one of our objectives. Okay, so we have discussed the single variable case. Let us discuss the multivariable case. So let us now consider this execution, which is our running example that we have been showing. So there are two threads, T1 and T2. T1 writes 1 to X, T2 writes 1 to Y. And then we read. So we read Y, T1 reads Y, it reads it to be 0 because the load is issued early. Likewise, T2 reads X to be 0. So can XY be equal to 0, 0? Well, in a modern out-of-order processor, yes. As per SC, no. So this order is clearly not sequentially consistent. Okay, this execution. But, let us look at this execution from the point of view of each location, right? So as I said, in such theoretical discussion, which is of course very important, the reason it is important is basically because without a little bit of theory, so when do you need theory? Okay, it's a broad, it's a philosophical thing, but when do you actually need a theory? So look at the night sky. So previously, when people didn't understand how really planets and stars move, They say that maybe you have Orion as a hunter and it is hunting a scorpion or a lion or a bull. So they created this notion of constellations, right? And then they said they gave a certain connotation to the pole star and so on. But when they started understanding things better, they found that everything could be explained with Newton's laws or Einstein's laws, and pretty much that could explain most of the movements of the night sky. Of course, this theory is not complete in the sense we do have dark matter and dark energy and so on. But that said and done, the objective of having a theory is to somehow explain experimental results, right, or engineering decisions and choices. So in this case, given the fact that we are looking at a very complex engineering system, unless we have some specification, we'll get lost. So we have already discussed that in our complex engineering system, this execution is valid. This is not an SC. But we still need a little bit of a theory to understand this better. That is why we created the notion of observers. And this is very important because every observer has a point of view. So we can always attach an observer per location where the observer only watches what happens for a specific location, right? So we can have an observer for X. So that would observe a write to X by thread 1 and a read to X from thread 0. As we have discussed in one of the assumptions in the previous slide set, the absolute times do not matter. So in any distributed or concurrent system, for such models, the absolute time, the wall clock time doesn't matter. What matters is diagrams like this. This is clearly sequentially consistent because we have a sequential order which is Rx0 and Wx1, which means that X was initialized to 0, I read 0 first and then you wrote to 1. Similarly, if I have another observer with respect to Y, again this is the execution that the observer sees. This is again sequentially consistent. Well, why not? Ry0, Wi1. So we do have per location sequential consistency because for both X and Y, they are per location sequentially consistent. So now we have an interesting example where overall we do not have SC, but we have PLSC. So which means SC does not imply PLSC. Oh, I'm sorry. It's the reverse. It's the reverse. Sorry. Sorry. We have PLSC, but we don't have SC. So this means that even if we have per location sequential consistency, it does not imply that the overall execution is sequentially consistent. So what does this mean for us? This means that even if we have a system with a lot of distributed caches, where PLSC does hold, in the sense the distributed caches appear as a monolithic shared cache for outsiders, it still does not guarantee that the overall system provides sequential consistency. And this is being captured by this example where you can clearly see that PLSC holds but SC doesn't. So PLSC does not imply SC. All right, let's keep moving. So then let's take a look at this particular execution once again. So in this case, we are assigning them to the temporaries T1 and T2, which are registers. So this outcome, as we said, is clearly not in SC. And so as we have seen, this is not in SC, but it's there in PLSC. So an important point needs to be said here that look, PLSC does not guarantee SC, but definitely SC guarantees PLSC, because if it is overall sequentially consistent, it is going to be per location sequentially consistent as well, because program order is guaranteed, legality is guaranteed, that will be there per location. So SC guarantees PLSC, so PLSC does not guarantee SC. So we can say that PLSC is weaker and SC is stronger. Now let's come back to the discussion. The reason why PLSC guarantees do not translate to SC guarantees is basically because the loads will be sent early to the cache, the stores will happen at commit time. So the loads will, in a sense, bypass the stores. If we still need sequential consistency, loads will have to be issued at commit time, which means we will not have out of order execution. All the benefits of out of order execution will go away, right? All the benefits of having an LSQ will go away. So pretty much everything that we have learned in the previous chapters on performance enhancement will be rendered to a null, right? So for high performance, we have to let go of SC, we will have to sacrifice SC. We may not sacrifice PLSC, right? So we will not actually sacrifice PLSC, but we have to sacrifice SC in the interest of high performance. Otherwise, many of these performance enhancing optimizations will not be possible. All right. So now let us look at some of the ways in which we can break SC, because SC anyway, as we have said, is meant to be broken. So SC is essentially atomicity of writes plus program order is equal to SC, right? So program order, as we have seen, is clearly being violated over here because of our out of order pipeline. Let's look at atomicity. So in atomicity, what is happening? Let's take a look at this execution where we write 1 to x. As long as x is not equal to 1, we keep looping in a while loop. So since we read 1 to x, ultimately it exits. Since we write 1 to x, ultimately this while loop exits. Then we write 1 to y. Again another while loop loops on y until it is 1. Finally it exits. At this point, what would you expect? You would see a clear path of causality, right? And then you would see a clear path like this. You would expect to read x to be 1, but let's say you read x to be 0. Okay. So then what I can do is I can create an execution like this. But let me assume the first time I access the while loop, I read x or y to be 1. So I never iterate. So then this would look like this. I write, I read. Then the next is a program order relation which has to hold, because unless I exit this, I can't execute this. And then again I write, I read. In this case, you expect to read 1, but you read 0. So what's happening? This execution is not in SC. Okay, that should be obvious. So if it's not obvious, you try to put it into a sequential order, and you will find that it is not puttable because there is a clear path and legality is being violated. This should read 1, it is actually reading 0. So there is a violation of legality. It's not in SC. It is, however, in PLSC. Kindly verify. Verifying it is very easy. So what you do is, for PLSC, you just create an execution for a single variable. So it's wx1, rx1 and rx0. Of course, it's in PLSC because I can order them sequentially. Rx0, wx1, rx1. Fine. What about for y? For y, I can do the same. So for y, what I can do is that I can have wy1, ry1. And this is also in PLSC because first this instruction executes and then this. So this is in PLSC. It's not in SC. It's one more of those executions which is in PLSC but not in SC. But there is a fun point. The fun point is that we are violating SC in a different way. In the previous slide, we are violating the program order constraint. In this case, we are violating the atomicity constraint. So it appears that the write to x, is happening at two different times. So thread 2 is reading the value of x, the updated value of x. Thread 3 is reading the old value. So since a write appears to be happening at two different points of time, it is non-atomic. So then, I mean, this complicates our life significantly, right? So you will say that, look, from the point of view of the observer who's only observing the accesses to the variable x, we have PLSC. What does PLSC mean? It means per location sequential consistency, which is again, it means that all the accesses to that location by a thread are in program order. Fine, I have no issues with that. But it also means that writes are atomic. Yes, but this is where the point of view matters. So the writes are atomic with respect to an observer who is only observing the accesses to variable x. But the writes are not atomic with respect to an observer who is observing the accesses to all the variables. Alright? So the point of view of both the observers is different. The point of view with respect to the observer who is only observing updates to a given variable, accesses to a given variable, from her point it is atomic. But when we consider accesses to other variables like y in this case, then the writes to x do not seem to be atomic. That is why we have PLSC, which is per location sequential consistency, but we do not have sequential consistency when we consider the accesses to y as well. So this is why memory consistency models are slightly tricky, because what really matters is observers and their point of view. So what did we learn? We learned that observers and their points of view are very important and crucial. So in this case, PLSC does hold, but SC does not hold because writes are not atomic. You can come back to me and tell me that, look, how did PLSC hold if writes are not atomic? I will tell you that, look, from the point of view of an observer who is only looking at accesses to x, writes are atomic. But when you consider multiple variables, writes to x are not atomic. So it's important that you understand this part, because this is very crucial in analysis of such systems, which is the notion of observers and their points of view. Okay, so anyway we did a little bit of analysis, so I have that in the slides, where essentially what I do is I look at the points of view of observers only for specific variables. So you can see that these are clearly in SC, right? So PLSC holds. Non-atomic writes, well, there are many popular architectures such as IBM machines and ARM machines where writes are not atomic, again for performance reasons. What is happening here? Thread 2 is basically reading the write to X early before it is visible to thread 3. This is possible if multiple locations store the variable X and core 2 is somehow closer to core 1 and core 3 is far away, so core 2 sees it first and core 3 sees it later. In any system with an NOC, this can easily happen. But nevertheless, as far as we are concerned, the execution is in PLSC. So let us accept it. If we are accepting non-atomic writes, and IBM and ARM's memory models do accept it. So you run something on your phone, you might very well see this execution. So this means that PLSC will hold. As I said, PLSC always holds if we want distributed cache to act like a shared cache. But atomicity might or might not hold. It depends on the memory model. So in Intel machines, atomicity holds, but in IBM and ARM machines, it does not hold. So let us now look at a behavior which is not in PLSC. So this behavior would be that I write 1 and 2 to X and I read them in different orders. So we have seen this execution before also, and this execution is not in SC. Since there is a single location, it's not in PLSC. We have also seen SC implies PLSC, PLSC does not necessarily imply SC. And we have also seen that writes that are atomic with respect to one location may not be atomic with respect to multiple locations when you are considering multivariable programs. So such kind of behaviors break the notion of shared memory completely, right? Which behaviors? So this is this kind of behavior, right? So the behavior of this, because PLSC does not hold uh, this behavior kind of breaks the notion of shared memory, because for any external, what will it observe? It will observe that, look, I wrote 1 first to x and then 2, but then everybody better observe that, right? If T3 is not agreeing, then it appears that x is not stored in a single location, and then essentially this does not make any sense. So we will allow non-atomic writes. Let us thus allow non-atomic writes of which kind? Oops, sorry, of this kind. Let us allow non-atomic writes as long as PLSC holds, which means that if I am only concerned about the accesses to a single variable, they should be sequentially consistent, and that will give me a lot of correctness properties of distributed caches, make them similar to shared caches. But of course, when I'm considering multiple locations, then what will happen is that writes may appear to be non-atomic, in the sense what's happening here. I'm writing 1 to x, right? I'm writing 1 to x. This write is quickly visible to thread 2, but it is taking much longer to propagate to thread 3. Fair enough, but how do we actually discover this fact? We discover this fact via accesses to other variables, right? Which in this case is y. But let us say that we don't actually consider this, and then let's say that at some point of time we actually read 1 in thread 3. All subsequent accesses will also give us 1, because the write has ultimately reached thread 3. So the main reason for this behavior is that, look, messages and accesses do take time in a realistic system, but if I were only to consider accesses to one variable, I will still see that writes are atomic, because we will never have an execution where the writes are actually not atomic. Okay, so we will never see executions like this where writes are not atomic. But what can happen is, the moment I consider accesses to other variables, then I can see the effect of a write, or effect of a write being read early via other variables. So what is the crux here? That I am seeing the effect of a write being read early via other variables. Okay. So basically, if I don't consider other variables, I will not see the effect of a write being read early, and that is why in this case PLSC holds, right? Because in PLSC I don't consider other variables, but if PLSC is genuinely not holding, as in this case, then clearly all observers will say that, look, clearly we are not implementing a correct memory system. So let us thus agree to allow non-atomic writes as long as PLSC is preserved, right? I mean, subject to the memory model. Some memory models might allow, might not allow, but let's say that we will not have objection to it, or we will not say that a memory model is invalid if it allows non-atomic writes, but PLSC we will never compromise. So we have decided to draw a red line. So PLSC, there is no compromise. Program order and atomicity, well, we will leave it to the processor designers. So what we are saying is that, look, you are a processor designer. Here are certain red lines thou shall not cross. One red line is PLSC, you will have to obey and observe. Other things like program order and atomicity, that you can break, okay? So that it all depends on what optimizations you are implementing, that you can possibly break, but PLSC don't touch. All right, so what's the summary till now? SC is atomicity plus program order. SC implies PLSC. PLSC does not necessarily imply SC. PLSC does hold in systems that have non-atomic rights, that have atomic rights. PLSC is needed to provide the illusion of a single memory location in a distributed cache. So PLSC, no compromise, the rest, possible compromise. So how do we move from PLSC to coherence, right? So PLSC to a large extent has taken us around 95%, in the sense it has told us that look, I have a shared cache where for every variable I have a single physical location, and then I have a distributed cache where for every variable I have different physical locations. For an outsider they will look identical if I have PLSC, which again can be broken down into per location, program order and atomicity. So program order would basically mean that processors or cache controllers are not allowed to reorder accesses to the same address. So that they would anyway do, because caches have FIFO queues for requests, so they already ensure program order in that sense. And also our pipeline needs to be modified such that we will not reorder accesses to the same address, but that we anyway don't do. Our load store queue ensures that we don't do it. So the next is atomicity. So because of PLSC, an observer at a memory address always sees atomic writes only for accesses to that address. But an observer on a different core, as we have seen, may see non-atomic writes because of intervening accesses to other addresses, right? So you take away other addresses, it should then become atomic. So for a given address, we have, let us define two orders. A global order is when all observers record this order between operations. So let us say we have one operation O1 and one O2. So if we have different observers in, let's say, different cores or in different sister caches of a distributed cache, everybody will record that look, O1 happened first, O2 happened later. Okay. So all of them will record. If all of them record and agree, so it doesn't matter if O1 happened before O2 1 second before or 10,000 seconds before, that doesn't matter. As long as they record such a happens before relationship, we say that this order is global. If let's say a few do and a few don't, we say that this order is not global, it is local. So let us now look at the ordering between accesses to the same variable across threads where the observer is at a core. Okay. So let us consider two reads to the same address. So their order doesn't matter because anyway they will read the same if there are no intervening writes. So we don't really care. Consider a write and a read. So what can happen is that given that a core can read another core's write early, while other cores may not even see the write, this order may not be global all the time. Correct? So what will happen is a core does not know when a write reaches the sister caches, the rest of the sister caches present in other cores. So I might say that look, I got a write and then I read, so I might record that order, but the others might not really agree. All right, hence another sister cache may not agree about the values read by other cores. Right, one core may not agree about the values read by other cores. Right, so this order is local. Let me explain with an example. So let's say I write 1 to x. So another core reads 1 and I read 0. Right, so then and furthermore there could be intervening accesses to other variables, so there could be a break in atomicity, but pretty much the key idea is that look, this order, so these are separate cores. Okay, so this order of wx1 to rx1 I might not agree that the write fully completed, which means that all the cores receive the value of 1, and then let me give these numbers 1, 2, and 3. Then core number 2 actually read it, right? So I will not agree with that. Even the core 2 will say that this write was fully completed, hence I read x to be 1. Core 3 will not agree. Core 3 might say that look, this write actually didn't. So I'll go back to that the slide that talks about this. So I'll erase the ink. So just look at this. So in this case, core 2 might say that look, this write fully completed, which means that the write was broadcasted all over the place. All the cores had x equal to 1, and I read x to be 1. But I am core 3. I might not agree that the ordering between the write and the read was global, because I will say that look, that's not correct. You read 1 early, but when I tried to read x, mainly because you read x to be 1, you set y to be 1, then I read y to be 1, and when I tried to read x, I read it to be 0. So I don't really agree that the write fully completed and then you read. The write was in the process of completing and you went ahead and read. So the write to read order, I will say that it is not global, it is local. Fair enough, since we allow non-atomic writes, there is nothing much that, there is no reason why we should have a problem. But the remaining two conditions are directly following from PLSC. So consider write to write. So consider two observers at two different cores. They cannot really record the fact, as you can see over here, that these writes happened in a different order. So T2 is recording that write to x equal to 1 happened first and x equal to 2 happened later. But T3 is recording that x equal to 2 happened first and x equal to 1 happened later. This means that x has ended up with two different final states. T3 says the final state of x is 1, T2 says the final state of x is 2. So this completely breaks the notion of there being a single physical location associated with x, right? So since they have two separate final states, we cannot allow the write to write order to actually get violated. So even if we consider accesses to multiple variables, right, uh, we cannot say that look, I mean, an observer at a core which is seeing accesses to all variables, but it's only recording accesses between two accesses to the same variable. It has to record a write and a write, two writes, right? Possibly issued by different cores. It has to record a consistent global order between them. If let's say one core says that I wrote x equal to 1 first and then somebody else wrote x equal to 2 after that, all the cores better agree, otherwise x will end up in two final states. So regardless of who issues the writes, this ordering has to be global. Okay. So what is this order again? Well, this order is between operations to the same variable, and these operations can be issued by different cores. So what we are saying is that look, for the observers, what are they going to record? So if there are two writes to the same address, which can possibly be issued by different threads, they will still record the same order, otherwise we'll end up with two different final states. Not allowed. Let us say that some core reads and some other core writes after that. So you read x equal to 0 and somebody else writes x equal to 1. Since writes are globally ordered, you will assume that one core records, let's say wi. So in a sense, I write 0 to x, then I read 0, then I write 1. If all the cores record that this read happened before this write, because the core that issued Ri could not have seen wj, else it would have read a different value. So what I'm trying to say over here is as follows. if let's say thread 1 read some value for x and thread 2 read some other value, thread 2 then wrote some value to x, if let's say another thread records that this read happened first and this write happened after that, can any other thread record it in some other way, right? So can any other thread record this specific interaction in some other way? What we are saying is that as a direct consequence of PLSC, there are more details in the book, but the crux of what I'm trying to say is that this is not possible. So what I'm trying to say is that both of these will be global and this is not possible. And the reason that I'm saying that this is not possible, because if some other thread has recorded that Ri, so let's say if some other thread has recorded a different order, for example, it has recorded that it has recorded the reverse order, it will have some reason for recording it, right? The reason is that it would have seen some path that I did the jth write, and then I did a sequence of actions, and finally thread 1 read x to be 0. See, if there are a sequence of actions between this write and this read, it clearly means that thread 1, given the global order of writes, would have been aware of this write, so it would have read the value that wj actually wrote. But that has not happened, right? That has not happened. It has read the value that has been written by a previous write. So given that that has not happened, we have a contradiction here, and it will never be the case that a read to write order between operations to the same address, albeit issued by different threads, will actually be local. In the sense, two threads will have conflicting views of the order, right? So that will not happen. So let me now summarize. So what I'm saying is that if I have observers at a core, at each core, so observers at each core will record what they are seeing, right? Pretty much what all they are seeing in terms of reads and writes. So the reads and writes can be issued by different threads, and they will record all of that. And let us consider all the records that pertain to a single address. So in this case, the observer at the core will basically say that, look, the read to read order does not matter, because in any case, if there are no intervening writes, it's immaterial, right? The write to read order, given that we allow non-atomic writes, will actually not be global. In the sense, an observer will basically say that, look, before a write was fully complete, you went ahead and read it. So I will not agree that the write actually completed first and then you read. And I might at best say that they are concurrent, but I will never agree that a given write happened and then you read. So go back to our example of three threads T1, T2 and T3, where we clearly saw a case where PLSC holds but atomicity doesn't. Now if we consider these two orders, so regardless of the fact that we are seeing accesses to other variables as well, a write to write order will always be agreed. Write to write order to the same address will always be agreed to by all threads. Otherwise, the same address might end up with different final states. And same is the case with a read to write order. So read and write are asymmetric over here, because let us say that we have a write to a given location, then we read its value, then there is a subsequent write. So all the threads will agree on this order. Why? Because if they don't, and one thread actually records this, then using this logic, Ri should actually return the value written by this write, but that is not happening, so there is a contradiction. Because of that, these two orders are global, and the first order is actually local from the point of view. So the point of view is important, extremely important. from the point of view of an observer at a core or on a thread, right? So if I were to summarize these things, the right to write order, right, is global. The read to write order is global. And the right to read order is global only for machines with atomic writes. Only if I have atomic writes, then all of us will agree that look, the write completed instantaneously and then another thread read. But if the write is not completing instantaneously at one point in time, the right to read order will not be globally agreed to, but the rest will follow from PLSC. So these orders will be agreed to by everybody. So the axioms of coherence can sort of be distilled from PLSC, and axioms of coherence basically say that writes to the same location, which essentially covers points 1 and 2, are globally ordered. In the sense, we all agree that for a given location, I wrote 1 first, then 2, then let's say 3, then 5, then 7, then 17, and so on. So there is no, between observers seated at different cores, there is no discrepancy in what they have recorded. Given that writes are globally ordered, the second follows. And coherence in that sense is mostly equivalent to PLSC, but coherence has one additional constraint, which is write propagation. The first is called write serialization, where serialization means putting it in a sequence. So we are doing that. And write propagation means that a write is eventually seen by all the threads. So writes are never lost, right? So write messages are never dropped by the system. They are eventually seen by all the threads. So these two are the basic axioms of coherence, where one follows from PLSC and the other follows from the fact that we never drop a write. Okay. So if we can ensure that our caches are coherent, so they would automatically follow PLSC because they are capturing the gist of PLSC. And in addition, they are also ensuring the fact that writes will ultimately propagate, reach their locations and complete. So now next we will discuss how to enforce sequential consistency, or how to kind of force sequential consistency in systems that have a wide variety of optimizations using what are called synchronization instructions. So SC using synchronization instructions would look like this. So let us look at some of the code that we have been looking at in the past. So what we have is we have value equal to 3. We set the status equal to 1. So this would be a typical way of communicating across threads, which unfortunately breaks if you do not have SC. So then we have a while loop which keeps on looping to see when the status becomes equal to 1. And the moment we see the status equal to 1, we read the value of value. This will unfortunately not work on a non-SC machine. The reason being that number one, the writes may be reordered if program order doesn't hold. That's point number one. Point number two is the write may not be atomic. So it is possible that this write at this point over here may not be visible. So because of this, this is appears to be a very easy way of transferring a value across threads, but this is not going to work. So you can try it and see. So this is not going to work with 100% accuracy. Had it been sequentially consistent, it would have worked, but it will not work. So the ordering between the read and write in T2 also may not hold. Also, as I said, atomicity is an issue. This store may not have fully completed. So T1 might have said that look, the store is done, but well, it might not have reached T2, while status may have reached. So that is why we add a fence instruction, where all the instructions fetched before the fence need to fully complete before the fence instruction executes. Which essentially means that if I have a fence, which I'll show in the next slide, This ensures that before the fence even you start executing, everything before it, reads, writes, everything, all the reads need to get their value all set, and all the writes should have committed, and not only committed, but the value should have reached all the cores, in the sense it would have fully completed, in the sense, and it would have updated all the physical locations that the variable is associated with. Furthermore, after the fence, no instruction in program order after the fence would have actually started its execution, right? All the instructions after the fence cannot execute until the fence instruction is completed. So all architectures support fence instruction, where they say everything before me fully complete, nothing after me starts. So how would this piece of code look like with fence instructions? The way it would look like is that we set the value to 3, we have a fence. So this ensures that when we set status to 1, the value is already fully written, right? It is also called globally completed or fully completed. But in layman's terms, what it ensures is that, look, when I write the status, the value is fully completed. And then when I read it over here, it basically tells me that status is 1, which means value is 3. And to ensure that these instructions are not reordered, I add a fence. So then if I add another fence over here, when I actually come here, I'm sure that this instruction is done. This instruction knows the status is 1. And because of the fence, we are sure that value has been set equal to 3. So regardless of the underlying memory model, whatever is respected in terms of program order or in terms of atomicity, it doesn't matter. This code will always work. So the way that an engineer is supposed to write parallel code is by inserting fences, and fences are expensive operations. So a fence would take 200 to 300 cycles. It's like a pipeline flush, in the sense everything before it needs to fully complete, and also everything before it we need to send, either we get acknowledgement messages from the memory system it's fully done, or we need to flush the write buffers and MSHRs such that no write is there in any temporary structure. So a fence is a broad is an example of a memory barrier. So a barrier is basically something that puts some sort of a precondition on the instructions before it actually executes. So there are many other kinds of barriers. So you can have what is called a store barrier. It will say that, look, before I execute, all the stores need to fully complete. I don't care about loads, but all the stores need to fully complete. Only then a store after me can begin. So in this case, instead of a fence, we can have a store barrier, which would be more efficient, right? So similarly, we can have a load barrier, which will be between two loads, right? So we can have barriers of different types. A fence is of course very generic. It does not differentiate between a read or write. It just says before me all complete, after me nobody start. All right. So we can have a special kind of fence operation. So these actually operate in pairs. So we will see the importance of this when we discuss critical sections, locks and unlocks. So there are two kinds of fences here: an acquire instruction and a release instruction. So an acquire basically says that when I want to start what is called a critical region of code, I have started with an acquire, which means no instruction after the acquired instruction in program order, which is essentially these ones, can execute before the acquire has completed. So I need to do acquire first, then everything after it starts, which means that either I acquire some permission or some lock, or we will see what exactly we acquire. But let's put it this way, that something needs to be acquired. Similarly, when I'm done with this piece of code, I call release. The release instruction can only complete if all the instructions before it, which means all the writes and everything, right, reads, writes, everything, have been fully completed. Fully completed for a load is when the result comes, and for a store is when the value is sent to all the cores. So note that the release instruction allows instructions after it to execute before it is completed. In the sense, instructions after it can execute before the release is completed. There is no issues. There are absolutely no issues in that. But acquire says nothing after me starts until I am done, and release says that I will finish only if everything before me finishes. So we will see this. There is a model called release consistency that uses this, but let's just remember it for the time being. Alright, so now we have discussed everything about sequential consistency, PLSC. So what have we discussed? We have discussed SC, we have discussed PLSC, and we have discussed PLSC and how it relates to coherence. We have discussed the two axioms of coherence, the serialization axiom, which means writes to the same location of a global order, and how exactly, what are the implications of that, and the fact that writes are never lost. So we write serialization axiom and a write propagation axiom. And then we discussed synchronization instructions, right? Sync. We'll call them sync. We'll not add a dot. We should, but we'll take a little bit of liberty with English. So we'll call them sync instructions. So now we have all the basic ingredients to dive right into the theory of memory model.